Hey, welcome back to chemistry. And so now what I'm going to do is I'm going to talk about a technique that will allow us to measure the amount of energy that is released in a reaction or is absorbed by a reaction. This technique is called calorimetry. So after I describe the technique, we will do a few problems regarding calorimetry. So first, let me talk about what calorimetry is. So here's an example. Let's say I have a chemical reaction that I'm interested in figuring out how much energy is released by. And so this chemical reaction is, again, one of our favorites, which is the burning of methane to produce carbon dioxide and water. So methane is CH4 and it can react with oxygen and produce carbon dioxide and water. And so because carbon dioxide and water are molecules with very little energy and methane and oxygen have a lot of energy, this is going to be a chemical reaction that's going to release energy. So you may be interested in the amount of joules of energy that will be released in this chemical reaction, say per every mole of methane burned. And so what you can actually do is, through a technique called calorimetry, is figure out that that number is 891,000 joules is released per 1 mole of methane that is burned. And so the way you determine that is through something called a calorimeter. So let me explain how that works. So there on the top right is we have a picture of a calorimeter. And so what you can see is really this rather large can. And it has some instrumentation from the outside that is sticking into the can. You can see that the instrumentation is kind of sitting in some water. Now, within the water, you have a smaller can. The smaller can is where you carry out the chemical reaction, and that smaller can is called a bomb cell. So the way the calorimeter works basically is you stick some kind of reactants into that smaller can, the bomb cell. In this case, it would be methane and oxygen gas. Now, as you might expect, methane will not react with oxygen gas without some kind of sparking. So for example, if you light up a Bunsen burner, you need a spark to get the flame going so that you can get the combustion into carbon dioxide and water. And so into that can, we will have a device that can send sparks through the can, and that will get the methane to react with oxygen and undergo the chemical reaction to produce carbon dioxide and water. Now, importantly, what will happen is with this particular reaction, it's going to release a lot of heat. The heat will leave the can and it will go into the water. Now, what you hope will happen is that any heat lost by the chemical reaction will be picked up by the water in its entirety. And the reason why you want that is because once the heat gets into the water, the temperature will get higher. And so once you know the difference in temperature, because you know the mass of the water and the specific heat capacity of the water and the temperature change, you can figure out how much heat the water absorbed. So again, importantly, what your big assumption in this calorimeter is that any heat absorbed by the water is exactly the same as the heat that is lost by the chemical reaction in the can. Okay, so at this moment, I want to sort of digress just for a second and talk about some terms that are used often a lot of times in thermochemistry. So we talk a lot of times about separating the chemical reaction from other things, and we might say the chemical reaction is going to be separated by putting it in this example, a can, and we can call the can a system. So the system is the place where the chemical reaction in this case takes place. Now, everything outside of the system, anything outside of the can, we can call the surroundings. So the water outside of the can and the rest of the calorimeter are part of the surroundings. The actual dividing line between the system and the surroundings is called the boundary. So the actual metal can itself can be thought of as the boundary between the system and the surroundings. So again, the major goal is to make sure that any heat of a chemical reaction that is produced by the system will go out into the surroundings and be completely absorbed by the surroundings. So again, we want to make sure that the amount of joules lost by the system is exactly the same as the number of joules picked up by the surroundings or absorbed in the water in this case. So what you really want to do is make sure that here where heat is symbolized by the letter Q, the heat of the chemical reaction that is lost by the system is exactly the same as the heat that is picked up by the water surroundings. And then also what you want to have to do is, because heat is lost by the system and heat is absorbed by the surroundings, then you have to have an opposite sign. So the Q of the system must be equal to the negative Q of the surroundings. Okay, another kind of calorimeter that you can use is a really simple one that you can make of coffee cups. So what I have here is I have 2 coffee cups. One coffee cup is placed inside of another coffee cup, and then you have the coffee cups are capped, and then maybe you might stick a thermometer in the coffee cup. And so what you can do is you can carry out a chemical reaction in the coffee cup and figure out, using the coffee cup calorimeter, exactly how much heat is released or absorbed by this chemical reaction. So the way the system and the surroundings work is a little bit different. So a good simple example to explain this is here on the bottom right corner. I'm sort of describing a situation where we may be adding a chemical called sodium hydroxide into water. So sodium hydroxide comes as these white pellets. And so when you have the sodium hydroxide pellets dissolve in the water, what will happen is the sodium hydroxide within those pellets will break out of the pellets, and then the sodium and hydroxide ions will go into the water and be dissolved in the water. It's sort of a standard dissociation reaction. Now, in that process where the sodium hydroxide pellets dissolve into water, releasing the sodium hydroxide ions, that is going to be an exothermic reaction, meaning a lot of energy is going to be released into the water. So how do we think of the system and how do we think of the surroundings? So the way we think about the system is we just kind of look at maybe the pellets themselves. That's where the sodium hydroxide is. And then for the surroundings, we look at just everything around the pellets. That would include the water. And so what we hope is that any heat released by the pellets when the sodium hydroxide is going into ions is going to be absorbed by the water surroundings. And so if we can figure out how much the temperature changes with the water surroundings, and we know the mass of the water and the specific heat of the water, we can figure out the heat absorbed by the water, which should be the same as the heat released by the sodium hydroxide pellets. And so in this case, because we have basically the chemicals being the system and the surroundings being the water, as you might expect, there really is no boundary here in a coffee cup calorimeter. So another thing you should be aware of is that a coffee cup calorimeter is called a constant pressure calorimeter. And the reason is this: when you carry out these chemical reactions in a coffee cup, the cap is going to be pretty loose. And so the pressure can get past the cap and then get into the solution. So the pressure is just going to be regular atmospheric pressure. Now, let's say you had a chemical reaction and it's going along, and let's say maybe the chemical reaction is producing a gas. So when you're producing a gas, you might expect the pressure around the chemical reaction to go up somewhat, to some degree. But because this is going on in a coffee cup calorimeter with a loose cap, any pressure that may temporarily go up will just basically go back down again, because the pressure of the gas will be released into the atmosphere. So as you're carrying out these chemical reactions in a coffee cup calorimeter, the pressure remains the same. So if that's the case, is all these chemical reactions are occurring at constant pressure. Okay, so now what we're going to do is we're going to practice solving some calorimeter problems. And so probably the most useful formula to use in calorimeter problems is that the Q of the system is equal to negative Q of the surroundings. So again, this basically says that any heat lost by the system must be gained by the surroundings. Now, in a lot of calorimetry problems, the surroundings is often the water. And so you could also go further and say that the Q of the system is going to be equal to the negative Q of the water. Now, many problems in calorimetry are concerned with transfer of some kind of heat from a very hot object into water. So a lot of calorimetry problems are where you put in a hot block of metal into water, and you're wondering, after the system comes to equilibrium, what the final temperature of the metal and the water are. So you can sort of imagine that process. The metal, which starts out as hot, is going to lose heat into the water. And then eventually, again, the metal and the water will achieve the same temperature. But any heat lost by the metal must be picked up by the water. Therefore, the Q of the metal is going to be equal to the negative of the Q of the water. Now, another thing you can do with these calorimetry problems is, if you need to, and this will have to be done most of the time, you will remember that Q is equal to the specific heat capacity of that matter times the mass of the matter times the temperature change of the matter. And so you can apply that to whether the Q is going to be, for example, the system, or the Q is going to be the surroundings. And specifically here, you can apply it to where Q is the metal, or here where Q is the water. Okay, so let's go ahead and give this problem a try, which is a very difficult and tedious problem. So let me kind of talk about what the problem is about, and then we'll try to solve it. So a piece of iron is dropped into 500 milliliters of water at 24 degrees Celsius in a styrofoam cup calorimeter. The final temperature of the water was measured to be 42.7 degrees Celsius. Calculate the initial temperature of the piece of iron. Okay, so this is a very difficult and tedious problem, so we're going to give it a shot here on the light bulb. Okay, so I think what might be good is for me to sort of draw a diagram for the problem, and that might give us a strategy for solving the problem. So here what we have is a coffee cup, and so we're given some information about what's going on in the coffee cup. So for example, we're told that the coffee cup has 500 milliliters of water, right? So no problem with that. Now, another thing that we're told is that we're going to throw in a very hot piece of iron. So here is the hot piece of iron here. And we're actually told the mass of the iron. So for example, the mass of the iron is 360.0 grams. Okay, so what I think we should do to help us solve the problem is try to decide what the system is, and then from that figure out what the surroundings are. So I suggest that we make the system the piece of iron itself. So the piece of iron is the system here. And so what you can imagine is that the water inside the coffee cup will be the surroundings. Okay. So that helps a lot with setting up the problem, because we know that any heat lost by the system, which is the iron, must be picked up by the water, which is the surroundings. So what we can do is we can write Q of system is equal to negative Q of surroundings. So again, you might be wondering why I'm writing a negative here. And the reason is because heat is being released by the block while water is doing the opposite, is absorbing that heat. And so we have to indicate a negative sign to show the opposite of the direction. Okay, so the Q of the system, we can write Q of the iron if we want, is equal to negative Q of the water. And so just to make my life a little bit easier, I'm going to say iron is equal to 1 and water is equal to 2. So we can go further in saying Q1 is equal to negative Q2. Okay, now at this point, what we can do is we can substitute the equations that tell us that heat is equal to the mass times the specific heat capacity times the temperature change. And so I'm going to go ahead and do that now. So remembering that Q, again, is equal to mass times the specific heat capacity times the temperature change, what we'll have is we will have M1 times C1 times delta T1 is equal to negative M2 times C2 times delta T2. So far so good with the setup. Now, what we may want to consider doing as well is we may want to recall that the delta T is just the final temperature minus the initial temperature. And so we could extend this a little bit more. So we could say M1 and I'm just going to leave out the times sign, but just know that there's a times sign there, times C1, and then delta T1 is what? Is TF1 minus TI1 is equal to negative M2C2 TF2 minus TI2. Okay, so let's see if we can substitute variables at this point and identify what an x may be. Hopefully we can solve for the x and solve the problem. Okay, so we are given some information. So again, 1 is the iron metal here, which is the left side of the equation. 2 is the water, which is the right side of the equation. And so we are told that the mass of the metal is 360 grams. So M1 is 360.0 grams. So we have that. Now, do we have a specific heat for the metal? Yes, we do. It's given to us in the problem. So the specific heat is 0.451 joules over grams degrees Celsius. So we're given that. And then we have a final temperature minus an initial temperature. Okay, so again, let's talk about the situation here is that we start out with a very hot piece of iron, and then I think what we're trying to find is what initially was the temperature of that iron before we dropped it into the water. But we are actually given a final temperature of the iron. And remember that in these kinds of problems, the final temperature of the iron will be the same as the final temperature of the water, because again, you have at the end of the experiment, all the heat that has possibly left the iron has gone into the water, and so that the iron and the water are the same temperature. So we are told the final temperature of the water in this experiment, so we should assume that it is also the final temperature of the iron. So the final temperature of the iron is going to be 42.7 degrees Celsius, and the initial temperature of the iron is actually what we're trying to find. So that is the x. Okay, so it's going to be equal to negative, so M2, let me put a brackets here. So M2 is, I guess, what, the mass of the water. Now, we're given a volume of water. It's 500 milliliters of water. Let's assume that the density of water is 1 gram per mil. So the mass of the water is 500 grams. And then the specific heat of the water here is going to be what? Let me get rid of that brackets there. That's confusing. Sorry about that. There we go. The specific heat of the water is going to be 4.184 joules over grams degrees Celsius. The final temperature of the water we are given, it is 42.7 degrees Celsius. And the initial temperature of the water we're given as well is 24 degrees Celsius. So what I'm going to do is I'm just going to plug in numbers into the equation and just see where the x is. Okay, so I'm going to have to get down here. So M1 is 360.0 grams, right? C1 is 0.451 joules over grams degrees Celsius. And then T final is 42.7 degrees Celsius minus x. So we're trying to solve for that. And then it's equal to negative, and then in brackets, M2, which is 500 grams. Looks like I'm going to need I think I'll fit it in. Times C2, which is 4.184 joules over grams degrees Celsius. And then the temperatures are 24 minus 42, or rather 42.7 minus 24. So actually you can put in that temperature change if you want. So it's going to be 42.7 minus 24.0, and I get 18.7 degrees Celsius. Okay, so we could spend about another 10 minutes solving this equation, but I think in the end, if you're very careful and do all the math correctly, the x should turn out to be 284 degrees Celsius. So again, the main concern about this problem is just the basic setup and then substituting the numbers in the correct place. And also remembering don't forget about the negative sign. For example, with the Q of the water, a lot of people tend to forget about the negative sign, and so they'll get a wrong answer. So remember, the Q of the metal is equal to the negative Q of the water. If you remember that the Q of the water is negative, that will help a lot. Okay, so let's move on to a final problem. Okay, so the next one is a little easier. Okay, so let's talk about the setup of this problem. So 50 mils of 1 molar HCl and 50 mils of 1 molar NaOH, both at 21 degrees Celsius, are added to a coffee cup calorimeter, and the temperature of the mixture reaches a maximum of 27.5 degrees. What is the amount and sign of the heat involved in the reaction? Okay, slightly different problem, but actually a little bit mathematically easier to solve. So let's just talk about the strategy of the problem. So here's the setup. We have a coffee cup again, and then here, let's say we have, what, 50 mils of HCl, and then we have 50 mils of NaOH. Okay, and so they will mix together. And so I'm going to draw this out in a different way. So I'm going to draw my coffee cup again. So let's just think of this as 100 mils of solution total. Now, to help us understand what the system is and what the surroundings is, here's, in my opinion, sort of a useful way to think about it. We want to figure out how much heat is being released by the chemical reaction of HCl reacting with NaOH. So I think the best way to solve this problem is to think of the system as the chemical reaction itself, while the surroundings would be just 100 milliliters of solution or water that's surrounding those chemicals. So here's the way you might think about it. So maybe think in the corner here. In this corner here, you have the chemical reactants. And so you have HCl reacting with NaOH. And so this will be a neutralization reaction. And it's going to produce water and NaCl. So think of these chemicals sort of in the corner, just the chemicals by themselves. And what is going to happen is they're going to release all their energy. Let me get a different color pen here. What they're going to do is they're going to release all their energy into the water. So what does this mean? It means the chemicals here, the reaction itself is the system, and the water in which this chemical reaction really is taking place is the surroundings. Okay, so we know that the heat released by the system must be equal to the heat absorbed by the surroundings. And so we can sort of write that out. So what I'm going to do over here is write the heat of the system is equal to the negative heat of the surroundings. Okay, so here, what is the heat of the system? The heat of the system is actually the heat of the chemicals reacting. So it's really the heat of the chemical reaction. So to indicate that this is the heat of the chemical reaction, I'm going to write Q reaction. So what is the surroundings? The surroundings is the water. So it's going to be equal to negative Q of water, or which is fine, or solution, whatever you want to call it. Okay, so at this point, actually, you can solve the problem. So here we are trying to find the heat of the reaction. And so you might remember that the heat of the water is going to be equal to the mass of the water times the specific heat of the water times the temperature change of the water. So we can write mass of water times specific heat of the water times the temperature change of the water. Okay, so the mass of the water we know. So we mixed 50 milliliters of a hydrochloric acid solution and 50 milliliters of a sodium hydroxide solution. So the total solution is 100 milliliters. And so again, we're pretending that the water in the solution is the surroundings. So if you have 100 milliliters of solution, you have 100 milliliters of water. So if you have 100 milliliters of water and the density of water is 1 gram per mil, so we have 100 grams of water. Now the specific heat of water is 4.184 joules over grams degrees Celsius, and the temperature change of the water it's just going to be the final temperature minus the initial temperature. The final temperature is 27.5 degrees Celsius minus the initial temperature. So it looks like the temperature change, I'm just going to write delta TH here, is 6.5 degrees Celsius. So let's also, one thing, you have to be careful. See, this is sort of a minor mistake I made, but I caught it, so good for me. So note that I forgot to put a negative sign here. Don't forget the negative sign. So the Q of the reaction is going to be equal to the negative of these numbers here. So don't forget that. Okay, I know you'll do better than I did. Okay, so anyway, so what will be the answer? It's going to be, we can first cancel out units. Grams will cancel out. Degrees Celsius will cancel out. So we'll have an answer in joules. So the answer should be 100 times 4.184 times 6.5. And so I think if you work that out, and this is a negative, right? So it's going to be equal to negative 2,700 joules, which is equal to negative 2.7 kilojoules. So this is the heat of the reaction. So importantly, the value of the heat of the reaction is negative. You can't forget that. And the negative tells you something, as you'll learn about later. Whenever you have a negative sign associated with a number for a heat of reaction, that means that chemical reaction is an exothermic reaction. Another thing you'll learn later is that here, this chemical reaction took place in a coffee cup calorimeter. And so as you know, these chemical reactions occur at constant pressure. There's a term you're going to learn later called enthalpy. So what enthalpy is equal to or related to the energy at constant pressure. So here, when you have the heat of the reaction, is also called the change of enthalpy, which is symbolized by H of the reaction. Is basically the same value. But we'll talk more about that in a future presentation. Okay, well, thank you for listening to that, and we will see you next time.